is a connected particle question with one of them being on a slope, one of them on horizontal ground. So B is 2 kilograms, P is 4 kilograms, light and extensible string, taut, passes over a smooth, small pulley. They can move. There's an angle of 60 degrees here, and both surfaces are rough. The system is released from rest, and the subsequent motion P moves down the plane. B does not reach the pulley. So let's add the forces. And I'm just going to I wanted to make the diagram quite big. I'm just going to bring it up a little bit so I can fit everything in. Okay. So first up, I'm going to deal with the forces on B. Well, we've got its weight, which is going to be mass times gravity, 2g. And then we've got the normal reaction force. I'm actually going to get rid of that because it's kind of getting in the way. But there's going to be motion that way. And this normal reaction force, let me call it the normal reaction force of B. In fact, there's no other vertical forces, so I'm going to straight away go ahead and say that that is 2g, the weight. There's going to be a tension because P is trying to pull B to the left, and it's going to experience that force through the tension from the string. And there's going to be a resistive force, which is acting to the right, which is our friction applied to B. Let's look at the forces applied to P. Again, the weight acting down. It's going to be 4g. A normal reaction force that's perpendicular to the slope. Okay, I'm just going to call that RP. That's not going to equal the weight because they're not going in opposite directions. This angle is going to be 60. There's going to be a tension that's trying to stop it just falling down, the slope without any other forces. The tension is going to try and keep it up. Capital T, they're the same. And then there's also going to be a friction acting up the slope, which I'll call FP. Okay, so I've done the forces on B in red, the forces on P in blue. They are different kind of systems. We're not going to be dealing with the system as a whole. They're going to be dealt with separately. I've already done F equals ma. Sorry, I've already resolved the forces vertically. Just did that straight away. Now we know it's moving to the left, so what I'm going to now do is look at B, first of all. That is the simplest system, to be fair, because there's not as many components to consider or anything. Like there's horizontal forces, that's what's going to be causing it to accelerate to the left. So I'm going to apply F equals ma to the left. And that means that T minus FB is going to equal 2A. Now because it's moving, I know that FB is going to equal, I didn't say this before actually, maybe I should add it now. I'll just do this in a different color. So I've got my coefficient of friction at B on like the ground where B is, and the coefficient of friction, let me do that again, where P is. Okay, and it's given that the coefficient of friction between P and the inclined plane is twice the coefficient of friction between B. So I'll call this one mu, and I'll call this one 2 mu. So that means that FB, which is equal to mu B R, is actually, RB rather, is actually going to equal 2g mu. So T minus 2g mu is equal to 2a. And this is an important equation, so although it's not my final answer or anything, I'm just going to put a box around it just to really highlight that. Now let's look at P. Similar sorts of things again. So now I'm going to resolve perpendicular to the slope. There's no acceleration in that direction. I'm going to get that RP is equal to 4g cos 60. Those are the only forces perpendicular to the slope. Cos 60 is actually a half, so RP is in fact 2g. I'm actually going to go straight ahead and write down the coefficient, the friction relationship here. So FP is going to equal mu P times RP, which in this case is going to be 2 mu from here, multiplied by RP, which we just calculated. So it's going to be 4 G mu. And all that leaves is me to, oh, I'm not resolving forces now. I'm going to apply F equals ma down the slope. So I will get 4G sine 60, the component of the weight acting down the slope, minus T minus Fp, which I've worked out, 4G mu, that is going to then equal 4a. And I've got a second equation. Okay, good. We're trying to work out t in terms of g, so I've got to somehow try and combine these. Like quite often, what I would do in this situation is add the equations to get rid of the t, work out the acceleration, and then put it back in. But I'm not going to here, not least because I think we'll end up with the acceleration in terms of mu, but also, yeah, because basically because it's quite complicated, there's mu involved. It's going to be better to try and eliminate a and mu, in fact. So we're going to take the first equation up here and times it through by 2. So 2t minus 4g mu is going to equal 4a. Because the thing about this is that now I've got the same thing here. So I'm just going to work out like sine 60 is actually root 3 over 2. So I'm going to get 2 root 3g minus t minus 4g mu equals 4a. And then I'm going to subtract them. In fact, I'm not going to do that. I think it's easier to understand by saying that 2t is 4g mu plus 4a. And then the bottom one is that 2 root 3g minus t is 4g mu plus 4a. Because what I can then do is just set these equal to one another. Because the right hand side is equal, the left hand side must be equal. So 2t, you could alternatively have subtracted them, you get the same thing. 2t is going to equal 2 root 3g minus t, which means 3t is 2 root 3g, which means t is going to equal 2 root 3 over 3g. Or you could write it as 2 over root 3g, but we've got a rationalized denominator here. So there we go. That is our answer for t in terms of g. Okay, right. Next part of this question, we're asked to essentially work out the deceleration of b after the string breaks. We're told when p is moving at 2 meters per second, the string breaks. In the 0.5 seconds after the string breaks, it moves 1.9 meters down the plane. And then we've got to look at b. Well, I'm going to get a new diagram down. And actually, we're now looking at when the string's broken, so it's gone. So we've got two separate particles, essentially. Let's focus on P for the moment, because that's where I've got some information. In fact, I'm not going to be using part A. I mean, bits that I've written are going to be useful, but I'm not going to be using the tension, because the tension is now gone when it's broken. So let's just focus on P going down the plane, because it's still got a constant acceleration. We're told it's moving at 2 meters per second, so that means the initial velocity is 2, and then the string breaks, and then in the 0.5 seconds, so that means we're going to now be looking over the next 0.5 seconds, P moves 1.9 meters down the plane. And that allows me to work out the acceleration of P from the moment when the string breaks. So I will use S equals ut, No, no, I won't because I don't know what. Yes, I will. I want to find out A. S equals ut plus a half at squared. 1.9 is going to equal 0.5 times u. That's just 1 plus a half times a times 0.5 squared. That's actually a half of a quarter, 1 over 8. So I get a over 8. So then a over 8 is 0.9. A is 7.2 meters per second. Now let's look at just gonna do that in a different color actually. But this is gone. So looking back at the forces, a lot of them are going to be the same when the string's broken. We've still got a weight acting down, and this angle is 60 degrees. We've got this normal reaction force, RP, which we showed was 4g cos 60. Actually, it was 2g. The tension's gone, but there's still a frictional force going this way. I think we calculated it before. It's quite easy to lose track, but there we go. It's 4g mu. So I can consider P again and do F equals ma acting down the slope. And we know everything apart from mu. So that's what we're going to find. It's going to be 4g sine 60 minus 4g mu equal to 4 times the 7.2 that I just calculated. I can actually just cancel out those 4's. Sine 60 is root 3 over 2. So root 3 over 2 g minus g mu is going to equal 7.2. Just taking this steady, mu g is then going to equal root 3 over 2 g minus 7.2. And to get mu, I'm then going to divide by g. Which gives 0.13133. Now we're not quite done because where was it? Determine the deceleration of B after the string breaks. But now we've got the coefficient of friction. So if we focus on B, remember they're no longer attached. They're not going to decelerate at the same rates as when they were attached. They were accelerating at the same rate. So again, we've got 2g acting down. We've got 2g acting up. It's moving to the right, but the deceleration is to the left. And it's from the frictional force at B, which I believe we calculated as well before. It was 2g mu. And we've just now worked out that mu is 0.13133. So 2g times 0.13133 gives me 2.5740. So applying F equals ma on B to the right, that's going to give me a force to the right. The acceleration is going to be to the right, which is the same as the deceleration. So I'll get 2.5740 0.740 equal to 2 times a. We just need to divide through by 2. That is our deceleration, 1.2870. Three significant figures, 1.29 meters per second squared. Okay, I like it. Slightly different question. Particular, bit using like suvat, in reverse to get back to the coefficient of friction, and then using it on the other particle. Well done.